Hello everyone, we are talking about logistic growth today, which is honestly one of the more useful things that we'll cover this year. And so you're given in that huge, essay of notes before an equation, and there's a lot of good information there, so I'd recommend you read through that. There's some good examples just to show you how this can be used. It's pretty applicable. But you're given the equation dp over dt is equal to some constant times p L minus P, okay, where P is like your population, K is a constant, L is your limit, okay, or your carrying capacity, sometimes it's called. Okay, so we're given that a population of fish satisfies this logistical differential equation, where we're given an initial condition, okay, an initial condition of 4,000, okay, so we start off with 4,000 fish. And now the easiest way to go about this is to get my equation to look like this, okay, get it in this form, right? So I have a p on the outside, and then I have a p on the inside, and honestly, it's better if everything is an integer. There's no fractions in here. So what I'm going to do is factor out a p, and I'm also going to factor out a 1 over 6,000, okay, because this p is just chilling by itself. So I'm going to factor out a p over 6,000. What that gives me is the p goes away, and then I guess 3 times 6,000 is 18,000, and then minus p. Okay, so k in this case is 1 over 6,000, p is p, L is 18,000, and then p is p. Okay, so what that means is L is my carrying capacity, so 18 is also my carrying capacity or my limit. Okay, so the biggest that P can ever be, or the biggest population that I can ever have, is 18,000. So that's my limit as t approaches infinity. It'll never go above that. Honestly, it'll never even reach that. Okay, so what is the range of my solution curve? Well, the range of values, well, I start at 4,000, so that's my smallest. Okay, and I actually exist at 4,000 because that's my initial condition. All right, P, and then the biggest I'll ever be is 18,000 because I found that to be my limit. Now, because this is a limit to infinity, it'll never actually equal 18,000 because you can never actually reach infinity. So I'm not going to put a line under this inequality. Okay, next I'm asked for what values of P am I increasing or decreasing, and then to justify. Well, I know that P of T is always increasing. Okay, well, how did I know that? Well, if you look over here, this is my derivative. Okay, so my derivative is equal to this situation here. Okay, now if you take a look at this, 18,000 minus p is always going to be positive. It's always going to be positive because we're never going to reach 18,000. Every number we'll plug in for p is going to be less than 18,000. Okay? And it's going to be above 4,000. That's what we found here. So any number I plug in here is going to be less than 18,000 or above 4,000, and so this is always going to be positive. Any number I plug in for p is going to be between 4,000 and 18,000, which are positive. So positive times a positive means that dp dt is always going to be positive. Yeah, I know that. Hey, it's always going to be greater than 0. So it's always going to be increasing. Okay, remember that relationship between derivative and original function. All right, let's keep going. Okay, then I'm asked when I'm concave up and concave down. Well, concavity always uses the second derivative. So let's find our second derivative. Right, and we have to do some implicit differentiation here. Because remember, p is a function of t. So when I do chain rule, I have to count for that and write dp dt. Okay, so this is my second derivative. Now I'm just going to factor out a dp dt. Right, and this is what I get. Okay, now from part C, I found that dp dt is always positive. It's always positive, or you could say greater than 0, however you want to write that. It's always positive, and so I don't really have to worry about this, because right now I'm trying to find inflection points. Okay, remember with concavity, you look for points of inflection. And you do that by setting your second derivative equal to 0. This is always going to be positive. It's never going to reach 0. So I don't have to worry about this. All I have to do is set 3 minus 2p over 6,000 equal to 0 and solve for p. Okay, and if you solve for p, you end up getting 9,000. So 9,000 is my potential inflection point. Remember, the way we check that is put this on a number line, right? And I take a value and I plug it into my second derivative, see what happens. Well, if you take a number smaller than 9,000 and you plug it in, you get a positive number back. If you take a number bigger than 9,000, you get a negative number back. What that means is before 9,000, I'm concave up, and after 9,000, I'm concave down. Now keep in mind your limits. Okay, so above 4,000 and less than 18,000. But so long as you plug something in within your bounds, okay, you should get concave up here, concave down here. All right, so we'll write our answer and then justify. I'm concave up from 4,000 to 9,000. And my justification is because my second derivative is greater than 0. I'm concave down from 9,000 to 18,000. And again, my justification is because my second derivative is less than 0. Okay, then I'm asked if I have an inflection point. Yes, I do. 9,000 was my inflection point. And my justification would be because my second derivative changed sign. Remember, it's not enough for your second derivative to be 0. It also has to change sign. So my justification is that my second derivative changed sign about p equals 9,000. Right? And let's try to sketch a graph. Okay, so I know that at 9,000, I have an inflection point, so I change concavity. I start off at 4,000, and my limit is 18,000. So I kind of have a horizontal asymptote here. I'm never going to touch it. So 4,000 to 9,000, I'm concave up. 9,000 to 18,000, I'm concave down. It's going to look something like this. You're always going to have this kind of S shape here with a problem with the given bounds. Okay, and then the question is, what happens if these change? What happens if my initial condition changed? So let's explore that. Okay, this time, notice my initial condition is 20,000. Okay, now I already know that my carrying capacity is 18,000. That means that I put too many fish in. Okay, this is too big. This is too big of a number. Hey, I can only account for 18,000 fish. I put in 20,000. That means that they're going to start dying, right? So, given that, I know some things. Okay, I know that from 18,000 to 20,000, I'm negative. I'm decreasing. Okay, I know this because, like I said, I'm over my limit. I'm over my carrying capacity. If you plug some numbers in into here, you'll get negative numbers between 18,000 and 20,000. And if you're negative, that means that your derivative is negative. Sorry, if you get negatives, keep in mind this is your derivative, so that means that your function is decreasing. Okay, so I know that I'm decreasing because dp dt is less than 0. I'll probably erase this here. Okay, so I'm decreasing on 18,000 to 20,000 because my derivative is less than 0. Okay, then it asks me when I'm concave up, and I know some things here. Okay, so keep in mind that this is what I found to be my second derivative. Okay, now in this case, my first derivative I found is always going to be negative in my given range here. So this is going to be negative. And same thing here. Okay, if I plug any number in for p that's in my given range, it's going to be really big. It's also going to be negative, which means that my second derivative is always going to have a negative times a negative, which means my second derivative is always going to be positive. Okay, my second derivative is always going to be positive because my first derivative is always negative, this part of my second derivative is always going to be negative. Okay, and so let's try to sketch a graph of this. Now again, 18,000 is kind of like a horizontal limit. I'm starting off with 20,000, and from 20 to 18,000, I know I'm decreasing and I'm concave up. So I'm decreasing rather quickly. And then as I reach my limit, I'm going to be decreasing at a decreasing rate. So I'm going to level off more towards 0 and then probably go under a little bit. And then I'll pretty much hug 18,000 for forever. All right, that's it for these notes. See you all later.